So if you are ready, then I can introduce you. So we are very happy to have Isabel Vogt from the University of Washington and Brown University, who will tell us about Brill Noether theory over the Hurwitz space.
Thanks, Izette. Okay, so it's really great to be here. Thanks for the invitation and to all the organizers for organizing this session. So what I'm going to be talking about is joint work with Eric Larson and Hannah Larson. And I just want to say right away, I'm very receptive to answering questions, so just feel free to unmute and ask me a question if you have any question at any point during the talk. Okay, so the basic setup here, the main question, is given an abstract curve C of genus G, can we understand the geometry of the space of maps of that curve to projective space PR of degree D? So just to remind you, if I take a general hyperplane, it intersects the curve in D points. That's this other discrete invariant, the degree D. So let's remember how these maps come about, how we parameterize these. So this is equivalent to the data of a pair, L and V, where L is a line bundle of degree D on the curve C, and V is a subspace of the space of global sections of that line bundle of dimension R plus 1 that's base point free. So if we want to understand this moduli space and we want to understand its geometry, it's very natural to understand the moduli space of line bundles of degree D on a genus G curve that could admit such a subspace V. So they do have at least R plus 1 independent sections. And that is the Brill Noether variety that I'm going to be talking about for most of this talk. So it's a subscheme of the Picard scheme, degree D line bundles on the curve, with the condition that my line bundle has at least R plus 1 independent sections. So it could have this base point free subspace of dimension R plus 1. Okay, so it's not that hard to show that this actually is a subscheme to give it a scheme structure in a natural way. It's very naturally a degeneracy locus of a map of vector bundles. So it's a very natural variety, and we can ask, I think, some very natural geometric questions about this variety. So first, when is it non-empty? So roughly that asks, when can my curve be realized as a degree D curve mapping to PR? And if it's not empty, what's its dimension? So in how many ways can it be realized as a degree D curve mapping to PR? How canonical is this realization? And then once you know those sort of first local questions, you can ask more about the local structure. Is it smooth? Is it singular? If it's singular, where do the singularities occur? How mild or how terrible are the singularities? Questions like that. And then when you know those local questions, you could hope to ask global questions about its global geometry. For instance, algebraic geometers love enumeration. So if its dimension is 0, how many points are there in that finite set? And does it have some interesting combinatorial structure that maybe tells us something? And if it's positive dimensional, is it irreducible? And the way I want you to think about this last question is that I've separated out for you two discrete invariants in this problem, which are the dimension of the projective space, this R, and the degree of the line bundle, D. And so this last question, this fourth question, is asking, is the pair R and D the only discrete invariants here, or do I need to specify more discrete data in order to get irreducible moduli spaces? Okay, so those are the questions that we're going to talk about today in various contexts. And in general, these are subtle questions that really depend on the geometry of the curve. If you sit down and try to work out some examples, you can see, say, if you have a curve that's a general curve, or you have a curve that's hyperelliptic, you can get very different behavior. I mean, the hyperelliptic case is Clifford's theorem, so you get very different behavior in those cases. But you might ask, inside of MG, maybe all the subtle, interesting, weird behavior happens in some proper closed subvarieties, and if I take a curve which is general in moduli, it's in some open subset of MG, then actually there's maybe a more uniform answer. And that is true, and that's that's borne out in sort of the crowning achievement of this theory of limit linear series on curves, which was developed in the 80s. And I'm going to take all of these results and squish them together and call them the Brill Noether theorem. So the setup is, let C be a general curve of genus G, so in some open subset of moduli. Then this Brill Noether variety, WRD, it has dimension, which is the expected dimension. Well, of course, its dimension can be at most G, and so really this means the min of this in G. So it's G minus R plus 1 times G minus D plus R. This quantity rho is called the Brill Noether number. And I want to point out that this R plus 1 times G minus D plus R, this is the expected codimension as a degeneracy locus of a map of vector bundles. So this says it occurs in the expected codimension. And you should read into this that when rho is negative, it's empty. All right, so that's the first step, proved by Griffiths and Harris. Then some more interesting local structure. So it's only mildly singular. It's normal and Cohen-Macaulay. And the singularities only occur along WR plus 1D. So remember these nests, WR plus 1D says you have at least R plus 2 independent global sections. So then, of course, you have at least R plus 1 independent global sections. And all the singularities only can occur along there. So I want to point out that this normal and Cohen-Macaulay actually are not that hard in this case. The real crux of this is that the singularities can only occur along WR plus 1 D of C. It's Cohen-Macaulay automatically because it's a degeneracy locus of a map of vector bundles occurring in the expected codimension. And then WR plus 1 D is always codimension at least 2 in WRD, from which you can get normality. So really the crux in this case was that the singularities could only occur along WR plus 1D. All right, so moving on to enumeration. So this was actually solved first, but only in a virtual sense because we didn't know the dimension statement of Griffiths and Harris. So the upper bound on the dimension statement. So when rho is 0, when the dimension is 0, it's a finite set of points, and the number of points has this explicit closed formula, but I want to phrase it in a different way that will show you some of the combinatorial structure that's lurking here. So it's the number of standard Young tableau on a grid of size R plus 1 times G minus D plus R. So it's no coincidence that those are the numbers that show up in this first part in the expected codimension. R plus 1 is the expected H naught, and G minus D plus R is the expected H1. So this is saying you have a grid size of H naught by H1, and the condition that rho is 0 is exactly saying G is this product. So these standard Young tableau, I have to fill this grid with the numbers 1 through G so that it's increasing along rows and increasing along columns. And every filling corresponds, numerically corresponds to a point in WRD of C, but actually if you use degeneration, you can actually see a correspondence not just of numbers, but of points. It's a very beautiful theory. Okay, so that's part 3. And finally, the irreducibility part. So when the dimension is greater than 0, it's irreducible, which can be deduced from a connectedness result of Fulton and Lazarsfeld for degeneracy loci occurring in the expected dimension, together with the smoothness result of Giesecker. So this is great. It's what our intuition tells us, that the only discrete invariance in this moduli problem should be the degree of the line bundle and the dimension of the projective space. So when rho is 0, this can fail because this number can often be greater than 1. But there is a sense in which you can still make sense of irreducibility. And that's that the points, that finite set of points, there's no way of picking out a subset of it that makes sense as you vary the moduli of the curve. Which is to say, you can take the universal WRD, which lives over mg, and in this rho equals 0 case, it's some generically finite cover of mg. So over some particular curve, the fiber is like WRD of that curve. And the statement is that this has a unique irreducible component that dominates mg. So this is a statement about this cover having transitive monodromy. And that was the last part of this package that was proved by Isabel and Harris in 1987. So I think this is a really nice, satisfying picture in this case. We have this subscheme for a general curve. It's of the expected dimension, it's mildly singular, and it's irreducible. It's a very nice picture. So what's the problem? Why am I not done with my talk? It's that in nature, curves are often encountered already equipped with explicit realizations of low degree. Like on the street, you're going to meet curves that are low degree covers of P1, not floor of G+3/2 degree covers of P1. And these low degree realizations can force the curve to be special. So this can force the curve to be special in moduli. And so the Brill Noether theorem might not apply. I mean, it doesn't apply in its stated form as I've said it. So the particular case that I already mentioned is if C is a cover of P1 of degree K, and K is strictly less than the floor of G+3/2, which is the expected gonality of a curve coming from the Brill Noether theorem. So for the remainder of this talk, I want to focus on this case. So we're not going to fix the data just of a curve of genus G, but a curve of genus G, which together with a degree K map to P1. So this of the curve and the map now lives inside the Hurwitz space of degree K genus G covers of P1. And I'm going to assume for the remainder of the talk that it's general in there, in that Hurwitz space. And then the main question now is going to be, if you fix this one map to P1, what can you say about the geometry of other WRDs in the presence of this fixed map? How does it affect those other WRDs? Any questions about the question before I move on?
What do you mean by the presence of the F?
I mean, yeah, I just mean that it's going to be fixed. It's going to exist. So the curve might be special, like a general curve of genus 7 is not going to have a degree 4 map to P1, something like that, you know. But I'm going to work with genus 7 curves that do have degree 4 maps to P1, and so it's going to exist and it's going to affect the other maps.
Okay, thank you.
I'm going to do an example next, so hopefully that will also clear this up a little bit or make it more apparent. Great question. Okay, any other questions? Okay, so let's do an example. This is everyone's favorite example. So we're going to work on a genus 5 curve, and it's going to be special because it's going to have a degree 3 map to P1. And I'm going to try to understand W14 of the curve. Okay, so it has a degree 3 map to P1, so that's the important thing. So let's write that down. So F is a degree 3 cover of P1, which means if I pull back the O of 1 on P1, this is a line bundle of degree 3 with H0 equal to 2. And so because this is so important, I'm going to give it a name. I'm going to call it H. But we want to look in W14 at other line bundles. So remember this 4, this is telling us we want line bundles of degree 4, so maybe line bundles L of degree 4, and this 1 here is telling us that we want H0 to be at least 2. In fact, it will have to be equal to 2. Okay, and we are handed this H, which looks like the L's that we want, except that its degree is 1 less. So we can build such L's by just adding a base point. So there's a component of W14, which is isomorphic to the curve itself, which is line bundles of the form H twisted up by a point P, where P is any point in the curve. Okay, but that's not all we have. And one way we can see that that's not all we have is by Riemann-Roch, if H0 of L is equal to 2, well, by Riemann-Roch, this is the degree, so 4 plus 1 minus the genus plus H0 of the adjoint linear series, so KC tensor L inverse. And on a genus 5 curve, KC has degree 8, and L had degree 4, so this whole tensor product has degree 4 again. And so what that tells us, because this little interior portion is 0, is that the adjoint bundle also has to be inside W14. And so it gives us another component, and I'm not lying here, you can show that they intersect in 2 points, another component of line bundles of the form KC tensor H inverse twisted down by Q for some point Q on the curve. And as I said, these intersect in 2 points. Okay, so this is the picture that you get for W14 of such a curve. And if you take a step back and look at this, it really doesn't look like the nice Brill Noether package picture I showed you before. First of all, it's not irreducible. It's reducible, has 2 components. It's singular, right? These 2 components meet at 2 points, but W24 is empty, so it's not singular along higher W24, so it has unexpected singularities. So what's going on, right? It's not totally clear. And in general, I mean, this is just the first sort of interesting example, but many authors, Copens, Martins, Ballico, Keene, Park, many people, basically since the end of the main Brill Noether theorem, we're working on these sort of questions about Brill Noether theory for curves of fixed gonality. And they observed that this can have multiple components, which can be of the wrong dimension, and it can have unexpected singularities. So it seems kind of wild, and I think it's safe to say that from their papers, you would think it's a kind of wild situation. But some big progress on this problem came not so long ago in 2 papers of Nathan Flieger and Dave Jensen and Drew Ranganathan, where they determined the dimension of the largest component of WRD. So these dimensions can be not what you expect, there can be multiple components, but at least the largest component, they determined what the dimension was. So that's nice, it gives an analog of the Brill Noether theorem in that case, but it's also a little bit unsatisfying because it doesn't explain these other components, like we have some missing discrete invariants that we don't understand.
Can you say? Can you say what is the dimension?
I'm going to. Don't worry, it's coming. It's coming. Yeah. Thanks. Great question. So I'm going to tell you the dimension of every component. I mean, I will state it. It's not my result, but so my collaborator Hannah Larson and Kaylin Cook-Powell and Dave Jensen in 2019 independently suggested that these other components could be explained by another discrete invariant, which is the splitting type. So to explain this, remember that we have this fixed map from C to P1, and we're looking at line bundles on C. So maybe we want to understand if these line bundles have at least R+1 independent sections to determine if they're in WRD. And so the splitting type is nothing other than you push forward this line bundle under this finite map of degree k. So now this push forward is no longer a line bundle, it's a vector bundle of rank k on P1, and the splitting type is nothing other than the isomorphism class of this vector bundle. But we can say that more precisely because of the Birkhoff-Grothendieck theorem. This isomorphism class, so this vector bundle is always isomorphic to a direct sum of line bundles. I'm going to write O of E1 up through O of EK, which I'll abbreviate by O of vector E for this tuple E, which is E1 through EK, and this is exactly what determines the isomorphism class. So it's always isomorphic to such a direct sum, and it determines the isomorphism class. Okay, so what I just wrote here is now copied on the next slide at the top. The splitting type is this tuple of integers, E1 through EK, and now we can define a refinement of WRD, where we keep track of this splitting type. So WE of C is going to be the locus of line bundles whose push forward is isomorphic to O of E or some specialization thereof. And specialization is just a combinatorial property in terms of the splitting type called majorization, which is about partial sums all being less than or equal to. So, right, so as I just said, the splitting type gives a refinement of R and D, and the basic reason that that is true is that cohomology, these dimensions of cohomology are the same for push forward under an affine map. So hi of CL is equal to hi of P1 of the push forward of L. And so if you apply that to H naught, you see that you can rework R from the splitting type. And if you apply that to the Euler characteristic and you know the genus, you can rework the degree from this. So what that tells us is that WRD of C is some union over splitting types E that satisfy these conditions of these Brill Noether splitting loci. So that is the sense in which we get a refinement. And okay, well, if we look at the left-hand side, this had lots of irreducible components we didn't understand. And now we have it written as a union of some things. It's very tempting to say that the splitting type gives you these irreducible components. It is that extra piece of discrete data that you need to get an irreducible moduli space. So let's see how that's borne out in our example that I just gave you, this first interesting example. So in this case, the push forward is a vector bundle of rank 3. And if you do that Euler characteristic calculation, you see that the degree is -3. So I'm going to be looking for 3 numbers, E1, E2, and E3, such that the sum of EI is -3. This is what I will be looking for to determine splitting loci. Okay, so let's look at this blue component first. Those are line bundles L of the form H, the pullback of O of 1 under the trigonal map, twisted up by a base point. So, so these line bundles L, the defining property of being in here is that if I twist down by a point, this particular point, there is a point you can twist down by so that it's, sorry, didn't mean to say that. I meant if you take H and you twist down, if you take L and you twist down by H, it's effective. That's what the point captures for me. And so using push-pull, that's the same thing as saying that the push forward of L twisted down by O of 1 is effective. And that's the same as saying that in terms of its splitting type, it has to have, its largest piece has to be at least a 1, right? So that when I twist down by 1, I get something that's at least a 0, so I get something effective. So its largest piece has to be at least a 1, and then the most generic thing is I just balance out the other pieces so that they sum to -3. So -2, -2, 1. So it's this or some specialization. Okay, so this loci is a splitting locus. It's W -2, -2, 1. And the other component is just the Serre dual. This is W -3, 0, 0. And they intersect at 2 points, which are the common refinement of those 2 conditions. They are W, so it has to have something as negative as -3, and it has to have something as positive as 1, so the remaining piece has to be a -1. So actually, it does explain, the splitting type explains this one example. That is everyone's favorite first interesting example. Okay, so now to answer the question about dimension. So it also explains some local behavior. So this is a result of Hannah Larson from 2019 and Kaylin Cookpal and Dave Jensen from 2019 and 2020. So the dimension of each of these pieces is the, well, the codimension is this quantity max of these differences, EJ minus EI minus 1 and 0, which can be written more compactly as just H1 of end of O of E. So this is the expected codimension from deformation theory for a splitting locus, for when the isomorphism class of this vector bundle stays the same. And that works out to be the dimension. And then furthermore, it gives some more local behavior. This WE is smooth away from WE prime, where E prime is some specialization of the splitting type E. So this is very nice. It answers 2 parts of the Brill Noether package in this case, but it still doesn't tell us whether or not this splitting type is the only remaining discrete invariant. And the reason is that these results, these are local results in nature, right? They tell you about the dimension or the smoothness, they're local results. And this question about irreducibility, that's a global result. And the global results were not accessible by the previous techniques for the following reason. So they argue by degeneration. So you're going to degenerate to some special curve that's reducible. And if you don't know that everything is a limit, then you can still tell local behavior. But if you want to know anything global, like enumeration or irreducibility, you're going to need to know that everything in the limit actually, so everything on the central fiber is in fact a limit. So you need to rule this out. And this is not specific to this Brill Noether splitting picture. This is true in general. And Isabel and Harris worked around this by proving a regeneration theorem for limit linear series. And it does not apply in this case, precisely because that theorem is all about dimensions being correct. It's a bunch of dimension counts, and the dimensions are incorrect here. There are very non-transverse conditions that cut out these splitting loci. And so we needed to develop a way of dealing with these non-transverse conditions, only keeping the essential conditions to be able to do dimension counts. And so we could prove a regeneration theorem for these limit linear series that work in our case. So we did that. That's the main technical heart of the paper. And then we get the following results. So F from C to P1 is a general degree K genus G cover, again. So first we can say a little more about the local structure. So it's only mildly singular, it's normal, and it's Cohen-Macaulay. And in this case, the normality and this Cohen-Macaulayness, they don't just follow for stupid reasons from the fact that the singularities can only occur along specializations, because there are codimension 1 specializations. So you really do have to show it can't be singular along the codimension 1 ones. And furthermore, it's not a degeneracy locus occurring in the correct dimension. So the Cohen-Macaulayness has to be proven also. And now onto global results. So when the dimension is 0, we have an understanding of the number of points, this enumeration problem. It again has a lot of combinatorial structure. So it can be phrased as the number of K regular tableaux, which are certain fillings that satisfy a regularity property, on a more interesting Young diagram called a K-core. So it's not a square, it's not a rectangular tableau anymore. It satisfies some convexity property, which gives this K-core definition, and it's attached to the splitting type. So from the splitting type, you make this K-core, and then the ways of filling it gives you the number of points. And again, there's an identification on points, not just on numbers, in the degeneration, which is, I think, very beautiful. And finally, when the dimension is positive, so when it could possibly be, it is in fact irreducible. So the splitting type does completely explain the discrete invariance of this problem, gives you an irreducible moduli space. And more precisely, or more on top of that, when rho is greater than or equal to 0, there's no, you can't pick out a subset of the points. So they're exchanged transitively. So the universal WE has a unique irreducible component that now dominates the Hurwitz space, because that's what we're working over, because we fixed the map to P1 as well. Okay, so I think I am exactly out of time, so I'll stop there. Thanks for the invitation, and I'll take any questions.
Thank you, Isabel. Thank you. And then, are there any questions?
Could you do something similar for smooth plane curves or something?
I'd love to. I think that's a great question. I've been thinking about it a little bit, but I don't have anything to say yet.
Any other questions?
Do you think that your theory applies for vector bundles? I mean, instead of taking a line bundle, take a direct image of of a vector
Another
bundle?
good question. I don't know the answer. I mean, I imagine it's going to be more subtle because just the standard Brill Noether theory for vector bundles is much more subtle. But a good question. I don't have an answer.